Inverse functions. An inverse function reverses or undoes what is done by a function. For instance, let's take our variable x, input it into our function f, and what we get out is f of x. If we want to reverse that, we take f of x, put it into our function f to the minus 1 of x, which is our inverse, and what comes out is x, our original input. Therefore, algebraically, we can write f to the minus 1 f of x is equal to f to the minus 1 of x, which is equal to x. Another way to look at inverse functions is to take a look at the mapping diagrams. In the first diagram, we have a going through function f and becoming b. So the domain goes through the function and becomes the range. For the inverse function, we do the exact opposite. So now the range has become the domain. It goes through the inverse function, which is denoted as f to the minus 1 of x, and the old domain now becomes the range. But this only works for a one-to-one function. Because let's take y equals x squared. 1 squared is 1, but also minus 1 squared is 1. So then when you put 1 into the inverse function for x squared, how does it know to go to either minus 1 or 1? In this case, you would have to restrict the original domain in order to get an inverse function. So remember, when dealing with an inverse function, the old domain becomes the range, the old range becomes the domain, and it only works for a one-to-one function. When sketching the graph of the inverse, all we do is flip over the domain and the range. So here we have 4 points. The first one being minus 5, minus 4. The second point being 0, minus 2. The third point being 3, 3. And the final point being 5, 6. So the domain becomes the range and the range becomes the domain. So minus 5 minus 4 becomes minus 4 minus 5. 0 minus 2 becomes minus 2, 0. 3, 3 becomes 3, 3. And 5, 6 becomes 6, 5. So we can now plot those points. So we got minus 4, minus 5, minus 2, 0, 3, 3, and 6, 5. So now if we join them up, and if you can see, what we've actually done is we have reflected the original f of x. So y is now f to the minus 1 of x,
And what we've actually done is we've actually reflected it in the line y equals x. So I've drawn in the line y equals x, and as you can see, the 4 points are a reflection of those points in the line y equals f of x. So therefore, the line y equals f to the minus 1 of x is a reflection of f of x in y equals x. And that's a very important concept when talking about inverse functions. Let's go through a typical example. The diagram shows the graph of y equals f of x for x between -6 and 2. 1. Write down a f of -6. So I go to -6, go down to the graph and see what comes out. So -6, down to the graph and across, and what comes out is -5. B. Find f to the -1 of -4. Well, what does this actually mean? This means, what do I have to put in f of x to get out -4? So I do the reverse process. So I go to -4 as my output, go along to the graph, go up and see what I would have to have put in. And the answer is -3. C. F to the -1 of -2. So go to -2 as my output and see what I would have to have put in. Well, I would have had to have put in 0. D. F of 2. So I go to 2 as my input, go up to the graph, see what my output is, and that is 4. Right, find the range of f. Well, that's my original graph. So my range goes from -5 to 6. So my range is -5 less than or equal to y less than or equal to 6. Find the range of f to the -1. Well, the range of f to the -1 is my domain of f of x. So my domain of f of x is -6 to 2. So my range of f to the -1 is -6 less than or equal to y less than or equal to 2. And sketch the graph. So I can inverse the 3 points that I've got. So 0 minus 2 becomes -2, 0. -6 minus 5 becomes -5, -6. And 2, 6 becomes 6, 2. So I can now sketch this graph. And there we go, nice and easy. And you can see that that is a reflection in the line y equals x.
If we want to find the inverse of y equals f of x, we follow 3 very simple steps. 1. We interchange x and y. In other words, we change x with y. 2. We rearrange our equation to solve for y. 3. We replace y with f to the -1 of x, which is our notation for an inverse function. We also must consider any restrictions on x and y. 1. Find the inverse of f of x equals 5x plus 2. Rewrite as y equals f of x plus 2. So the first thing we do is interchange x and y, so we get x equals 5y plus 2. We now solve for y, so therefore we get x minus 2 equals 5y. Therefore, y equals x minus 2 over 5. So to write it as an inverse function, replace y with f to the minus 1. So f to the minus 1 equals x minus 2 over 5. So the inverse of f of x equals 5x plus 2 is equal to f to the minus 1 equals x minus 2 over 5. Number 2, find the inverse of f of x equals 4x plus 6 divided by 5. So rewrite as y equals 4x plus 6 divided by 5. Interchange x and y, so you get x equals 4y plus 6 over 5. Solve for y, so you get 5x is equal to 4y plus 6. Therefore, you get 5x minus 6 equals 4y. Therefore, y equals 5x minus 6 divided by 4. Replace y with f to the minus 1x. So you get f to the minus 1 of x equals 5x minus 6 over 4. So the inverse of f of x equals 4x plus 6 divided by 5 is f to the minus 1x equals 5x minus 6 over 4. Question 3. Find the inverse of f of x equals 4 divided by 2 minus x. So replace f of x with y. So we get y equals 4 over 2 minus x. Interchange x and y. So we get x equals 4 over 2 minus y. Rearrange. So we get x 2 minus y equals 4. Divide by x, so you get 2 minus y equals 4 over x. Rearrange to solve for y, so you get 2 minus 4 over x equals y. Replace y with f to the minus 1 of x. So you get f to the minus 1 of x equals 2 minus 4 over x. So the inverse of f of x equals 4 over 2 minus x is equal to f to the minus 1 of x equals 2 minus 4 over x. In this example, we have a restricted domain for f of x. 2 minus x cannot equal 0. Therefore, x cannot equal 2. Question 4. Find the inverse for f of x equals 3x plus 1 divided by 2. Replace f of x with y. So that y equals 3x plus 1 over 2. Now interchange x and y, so we get x equals 3y plus 1 over 2. Solve for y, so we get 2x equals 3y plus 1. So we get 2x minus 1 equals 3y. Therefore, y equals 2x minus 1 over 3. Replace y with f to the minus 1 of x. So we get f to the minus 1 of x is equal to 2x minus 1 over 3. Therefore, the inverse of f of x equals 3x plus 1 over 2 is equal to f to the minus 1 of x equals 2x minus 1 over 3. The horizontal line test. The horizontal line test tests if a function has an inverse. Not all functions have an inverse. In some functions, in order to have an inverse, we need to limit the domain. Take the graph of the equation x plus 1 all cubed plus 2. If we perform the horizontal line test, we should be able to draw horizontal lines anywhere on the graph, and the horizontal line will only touch the graph at one point. As you can see here, we have drawn 3 horizontal lines, each of which only touches the graph at one point. So this graph passes the horizontal line test. So the equation f of x equals x plus 1 all cubed plus 2 does have an inverse. The inverse of the graph looks like this. And as you can see, the inverse passes the vertical line test, so is a function. Now let's take the graph of f of x equals x squared minus 1 and perform the horizontal line test. When we perform the horizontal line test, the function fails. There are many occasions where the horizontal line will touch the function in 2 places. This means that the graph of x squared minus 1, or the function of x squared minus 1, does not have an inverse. In order to have an inverse, we have to limit the domain to either positive integers or negative integers.